Primitive Pythagorean triples, the Pythagoras equation, the quarter squares rule, and negative Pythagorean quartet, d squared equals c squared plus b squared minus a squared. My motto? Plain honesty, simple truth, easy understanding, the joy of finding things out for yourself. In the Euler archive, document E796, Leonhard Euler researched negative Pythagorean quadruples, but his methods were complicated, hard to follow, and whilst discovering what I can only consider some amazing quadruple groups, the overall count was rather small. The Euler archive document E776 on fourth power quadruples is in Latin, not my forte, and the numerical results are not meaningful to me without intelligible text. The Fibonacci identity must have been known to Euler, but there is no apparent use of it by him in the two archive documents. It is an obvious source of infinitely many negative quadruples. If we divide the area of the two rectangles formed by the diagrammatic proof of the Pythagoras theorem by 4, we have 4 smaller rectangles that form the square for one of the proofs for the quarter squares rule. The sum of the two sides of one of the rectangles add to give the side of the outer square. Subtracting the combined area of the 4 rectangles from that of the outer square gives the area of the inner square. I derived the numerical steps back in May 2014, but it was only a month or so back that I realized that the 4 integer squares produced always result in a negative quadruple for every primitive Pythagorean triple as input, hence this video. Keep the base numbers 7, 5, 5, 1 in mind for later. Here we see the numerical steps for the first 4 triples of the first primitive Pythagorean triple series and the first 5 negative quadruples that result. This is an odd series, so the 4 squares arranged in order of descending magnitude. This slide just gives the negative quadruples produced by the second and third primitive Pythagorean triple series, both of which are even series. Hence, the third square in the sequence has greater magnitude than the second. Here we have 2 infinite series of negative Pythagorean quadruples that both start with the triple 5, 4, 3 plus 1 term equal to 0, which were obtained by totally different means to the previous quadruples. Notice that the difference between corresponding base numbers for consecutive quadruples of the second series is 7, 5, 5, 1, which is the same as that for the first quadruple of the first Pythagorean series. Coincidence? Nah. Finally, I reckon that if Leonhard Euler came back today, he'd be peed off and mad about his paucity of negative Pythagorean quartet stroke quadruples in his researches, clever though they are. Furthermore, since he produced a proof of Fermat's statement that primes of modularity 4n plus 1 are the sums of 2 squares, this is just rubbing salt into his wounds, since they too are a rich source of negative Pythagorean quadruples. Leonhard Euler did discover the smallest Diophantine all-fourth power negative quadruple, 158 to the power 4th equals 134 to the power 4th plus 133 to the power 4th minus 59 to the 4th. I completed the trio and discovered its siblings, which are given below, both of which just fail to be an all-fourth power quadruple due to the 1952 square term.